Yes, hello there. My name is Makinde Abiani, and I'm going to take you through a single model architecture for scalp pathology detection. So here we are going to look at the introduction, the related work, the problem statement, research questions, all these things, references, and also the acknowledgement. So we are saying that generally, trichology is a branch of dermatology which focuses mainly on the hair and scalp health and also its diagnosis. Very many people worldwide are being affected by hair and scalp disorders, yet the diagnosis is subjective because of the visual inspection by specialists, variability in outcomes, which leads to the inconsistent results. So that is what we call the traditional approach. So we came in to address this gap by bringing in the modern revolution, which involves the use of image datasets, plus also the machine learning algorithms or models. So our goal is to get objective, standardized, and scalable trichological assessment. So we have seen that in related works, convolutional neural networks has outperformed the manual inspection in detecting hair-related diseases, and that involves the field of follicle classification, the probability generation, and also the multitask neural networks for severity estimation. So it has really outperformed manual inspection, but again, it has key challenges that are not yet addressed. That is data diversity, the annotation quality, and also need for clinical validation, which is very expensive. So we are seeing the problem statement whereby in the domain application problem, that is the healthcare context, we are having the hair and scalp disorders being manually diagnosed by the trichologists or by the experts. But this is subjective time consuming and also inconsistent across practitioners. Then in the machine learning context, that is the computational problem, we see that the problem you're having is not even just building the models, but the main problem is having to be able to build a trustworthy pipeline from which will help us from from the point where we're having the raw data to the point that we shall be able to use the information we've gotten to solve the problems we are having. So the research questions we had to ask ourselves how the environmental stresses like the UV exposure, they how they affect the scalp integrity and also hair health. Then also we had to look at the external factors in our data set, how they correlate with the observable scalp and hair alterations. Then also looked at how effective are current diagnostic imaging techniques combined with machine learning workflows in detecting the early stage disorders. So our research objectives, that is to explore and pre-process scalp image datasets. So we got our datasets and we had to explore them so that we can be able to understand them. Then we can use them in our project. Then the other one is to evaluate the proposed semi-supervised framework against fully supervised baselines. So we had to come up with a semi-supervised model. So our objective was evaluation of the framework, then to assess the clinical applicability of the developed models. So we also wanted, our objective was to be able to get a solution for the problems we were working on, and that is the scalp and health disorders. So the research contributions, the semi-supervised learning for early detection. So we developed using a small set of labeled images and a larger pool of unlabeled data. Then a single model combining trichoscopy images and scalp microbiome data. Microbiome data, that is the information about when you talk of microbiome, that is the bacteria which is on the scalp or on the head. Then 20 interpretability visualizations created. So we created these visualizations so that we can be able to have a wider picture or have a wider view of the image datasets and patterns which were involved in these datasets. So we have the number of annotations per class, and we're seeing the dandruff was the highest here. Then these ones were were low. Then even here, percentage of annotation per class, we saw that dandruff was dominating all their classes. Then bounding box center heat map, this one shows if we're having an image, which part of that image was mostly being found with the annotation with the scalp conditions or diseases. So we are seeing that most of them were on the center right. So the 94 and 45, 89 and 112. So most of them were at the center right. So I also looked at the imbalance ratio per class, whereby we saw that still dandruff had a higher ratio per class more than all these other classes. And here, cumulative annotation coverage, the Pareto chart also shows us how increasing were the datasets. So we started with the dominating classes, that is dandruff, then we went with the follicularis, alopecia, contact, and others. So we saw that these four were already dominating, and just with four classes, we were having 80% of the of the data set. So these are the model architectures. This is the efficient net B3, whereby you input in an image, the image information is expanded, then the features are extracted, then this squeeze excitation will get those features and be able to get the useful information from it. Then the convo one is going to resize the image back to the normal size, which is manageable. Then we can add a residual, which residual is like the information, the original information is added back so that the model cannot forget which information it was using originally. Then this is how it works. So having also the VIT, your input an image, scalp crop, then it is going to split this image into very many features. When it's split into very many patches, and for these patches, for all of them, we shall have an extra summary patch we add in front of them, and this is called a class token. This class token will absorb all the information for all these patches as they are passing through the model, or as they're passing through the different stages of the model. So this information is put into the transformer encoder, and the transformer encoder runs 8 times, and it undergoes two parts. That is the multi-head self-attention, where each patch asks the other patch whether they are related or not. Then the add and layer norm come after each stage so that they can be able to resize the image back to its manageable size. Then the feed forward ML or MLP, this one this one passes the information to the add layer node. Then we have the extract CLS, so the information which was got from the different patches. Remember, they are here and they are summarized. So this one is like it is like a vector of the image. Then that information is put into the MLP head, and then taken to the softmax, which gives us a final output of the 9 scalp condition classes. So this is the faster RCNN. Here we are having the information input, then the features are extracted. After extracting features, feature map, which is going to show the features which have been extracted. Then region proposal network. This one is going to tell us, is going to label those regions which it suspects to be having the conditions. Then the proposed regions are going to be taken into the region of interest. So this one is going to pick out the regions which are needed by the model to work. Then fully connected heads. Then afterwards, we shall have classification, which is going to tell us which conditions are available. Then bounding box is going to draw a bounding box or a rectangle in the area which is affected. Then we shall have an output. So that is faster RCNN. Then for Mac RCNN, it is also the same. You input the image, then we're extracting the features. Those are the edges, maybe the colors. Then those features are going to be put into the region proposal network. It is going to tell us which regions it is expecting to be having the conditions. Then we shall have the shared fully connected head. Then the information there is going to be divided, whereby we shall have classification telling us which conditions are which are affecting the scalp. Then the bounding box, it is going to draw the rectangle into that place which is having the conditions. Then the fully convolutional mask head, then we shall have the final output. So that is the mask CNN. Then for the RRT, this transformer, for it, you are going to have the image. Then you input it. After input, the features will be extracted. Then you have hybrid encoder, which is going to there is feature fusion, whereby you're going to get all those features and put them together, but you're getting them from the different areas of the scalp. Then self-attention, each patch or each feature is going to ask the other feature whether they are related or not. So the information got from the hybrid encoder is going to be used by the transformer decoder so that it can be able to get information, which information is going to be used by by part matching. Then we shall be able to get the final detection. So then this SVM, for it is there to, when it gets the image, it is going to divide the image into different pieces. Then this PCA is going to, remember, scalp crop image is input. Then this one is going to extract the features. After extracting the features, it is going to, the PCA, principal component analysis, is going to remove all the useless features. Then it leaves only the features which are useful and needed. Then the RBF canal is going to take those features into a high dimension, whereby in case we are having some conditions which are looping, they are going to be separated very well, so that that can be used to get a max margin. Then a decision can be made for which margin, where to put the boundary or margin in between those different scalp conditions. Then we shall get the output. So for the classification model accuracy, we are seeing that VIT dominated, had a higher accuracy than the SVM and the CNN. Then in object detection, we saw that faster RCNN had dominated in the accuracy. Then this is the VIT per class F1 score, with contact dermatitis having a higher F1 score, and alopecia. Then the rest are following. So here we are having a classification report whereby for each class we are seeing the precision and the recall. So for the recall, it is telling us out of all the things which are right, how many things did it output as right. Then for the precision, we are seeing that out of the things which are around, which the ones it is saying that they are true, are they really true? So then the SVM is also telling us the class, the precision, the recall, and F1 score. F1 score is a balance between the precision and also the recall. So when we had our model, let me say the YOLO V8, we had to prune it because there are some features which are not really needed during our deployment. So we had to prune some of those features. Then for the knowledge distillation, we are seeing that for the knowledge distillation, we had a VIT teacher and also the VIT student, or call it a CNN student. So when you input an image, the VIT teacher can be able to give us maybe the conditions and the confidence levels. So this CNN student, it learns from the VIT teacher, and also it learns from the fact that how able is it to tell the right thing, or the right output. So that is how it lands. So we are having a trained CNN, the edge deployment. Then so this after having the knowledge distillation, we can be able to have a CNN student, call it a model which is lighter and can be able to be deployed even in rural areas. So we are saying our data description got our data from RoboFlow, and it had a high resolution Scalp imaging data. So our focus was on ML-based diagnosis of common scalp hair disorders. So in our EDA, we saw that we had class distribution whereby we noticed class imbalances, like dandruff was so high. Then the image characteristics, whereby we assessed resolution, brightness, and color consistency. The annotation quality bias detection and also visualizations were generated. So we are saying that after completing the EDA, we had to shift to preparing the dataset for modeling, and this involved standardizing the labeling, cleaning metadata, and also fields for files into consistent structures for smooth pipeline integration. So our next step is standardizing and cleaning, then handling class imbalance, because we saw that dandruff was too much. Yes, so if we handle that, then we shall be able to get a model of higher accuracy, then normalization and data loader verification, then plus baseline scripts and runs. So in conclusion, we are saying that we have been able to demonstrate the potential of semi-supervised learning because we used images with few labeled data, then plus the aligned data set with unlabeled data. So the limitation we got was annotation scarcity, whereby we had a limited availability of fully labeled scalp images, then data set imbalance, as we've seen dandruff dominating other classes, then model constraints, then and also clinical translation. So our source of data set was the RoboFlow, and collaborative tools and platforms were was supported by the use of Cargo for the data set access, and TensorFlow for preparing our information. Thank you for listening.